Hi, my name's Trevor. I'm the author of Lamuna Engine, a light 3D game engine featuring a software renderer which you just saw running. Today I'd like to talk about the engine's dynamic light maps. Lamuna Engine features dynamic light maps which allow for the real-time world painting effect which you just saw in the demo. The light maps are low-resolution textures of uniform texel density applied to static world surfaces which can accumulate colour from light emitters. I originally conceived of the light maps as a low-resolution real-time lighting scheme for the world map to complement per-vertex lighting on the models, but when I experimented with the painting effect, I liked it so much I retained it. We start by assigning light map textures to each model that comprises the world. So here we step over each model, and using our Lexel, that is a light map pixel, Lexel to world space mapping, compute the size of each texture needed for each of the 6 faces of the block. We snap these dimensions to a power of 2 and create the texture, allocating memory for the light map from our memory chunk and allowing space for its mip-map chain as well. We create indices to the texture in our light map data structures. The Lexel to world space ratio controls the Lexel density of the light map, with high numbers increasing fidelity at the cost of increasing the number of pixels that need processing in real time and increasing memory requirements. Processing the light maps in real time is computationally intensive, so to ease the load I keep both a read and write copy of each of the light maps. This double buffering means the last frame's copy can be read from by the renderer while the current frames is being generated. This of course comes at the cost of doubling memory requirements and having the light maps lag 1 frame behind the game update. This section of code creates a copy of the light map data we just initialized. The second step in setting up the light maps is to compute the gradients that map from world coordinate space to local light map space, which will be needed for mapping our light source position into light map space. The final step is to apply a base texture to the light map. Since the light maps are the only texture applied to the world surfaces, they need to contain some visual detail. Light color is accumulated over this base texture. This code loads in 4 different world textures and distributes them evenly across the light maps and down their map chains. So now we turn to the real-time processing of the light maps. The process of updating the light maps each frame begins by determining which light emitters are casting light on which world blocks. Light emitters are the projectiles and particles and are identified in the entity component system with a light source component. This process is accelerated using the bounding volume hierarchy created during setup, where the static world blocks have been binned to a bounding grid, partitioning up the world into nodes which can be checked and trivially rejected. Since both the nodes and the world blocks are axis aligned, a simple overlap test against the light volume suffices. Here we use SIMD to process 4 grid nodes at a time. We broadcast the light source data out ahead of our loop, and then within the loop fetch out 4 node positions and extents into these array of structures, transpose them into structure array form for vector processing. Our bounding box check is done with vector intrinsics wrapped in these overloaded operators to make the code look and flow like scalar operations. We use a sparse array compression scheme on our result vector to output the index list. From the list of nodes each light source intersects with, we now generate a list of world blocks by performing the same process as above on the blocks within the nodes. Our output is a list of light sources with the world blocks they will light, but we actually want the data round the other way, that is a list of blocks with associated light sources. Since light map processing is threaded, we want each thread to have exclusive access to a light map or group of light maps. By processing world blocks against light sources we achieve this. This code performs that list inversion. As I mentioned, light map generation is threaded, where the processing of a collection of world blocks and their associated light sources are characterized as a job and submitted to the thread pool. This is the entry point for the thread. This function does some data unpacking and initialization, and then calls the workhorse function process lightmap bin here. This first section of code determines which faces of the block are illuminated by which light sources by culling back-facing surfaces. Using this information, we copy over the touched light maps from the read copy to the write copy, ready for processing. The modus operandi of the main algorithm is to compute a color contribution from the light source for each pixel in the light map based on the distance to the light source and its intensity. Instead of a radiosity calculation per pixel, however, the process contributes color to a surface by way of a projected texture, of which you can see an example in the text file below me. This is a grayscale texture that describes light intensity fall-off in 2 dimensions. If we imagine instances of this texture lying on the plane of each of the principal axes and centered at the light source, we can see a 3D position in world space can be mapped into this texture to obtain a light intensity value, where the Z component is used to attenuate the U and V components. This is similar to the process Doom 3 used for its real-time lighting, and is a neat way of avoiding complex radiosity calculations while giving artistic control over light properties, particularly fall-off. To avoid having to visit each pixel on the surface, we compute a bounding rectangle for the light's extent in the lightmap space, clamp it to the lightmap dimensions, and iterate over it. Lighting computations are performed on the highest MIP level. Once all the lights affecting a surface have been processed, we propagate the updated light map down the MIP map chain. We track which light maps have been touched as part of the update process. At the end of this frame, the read and write references for those light maps that have been updated are exchanged in this buffer swap function. Well, that concludes our look at the dynamic light maps. Be sure to check out my code reviews of other engine systems, visit my website, and follow me on Twitter. Thanks for watching.